Hey guys, today we're going to talk about nature of light and how light acts and what causes it to act that way. So there are a lot of unanswered questions about the atom and elements in general, and scientists came to observe that certain elements emitted visible light when heated in a flame. So if they took a sample and they put it in a fire, it ended up glowing a different color. So those colors were able to give us information about the chemical behavior and characteristics of those elements, including the arrangement of their electrons. So fireworks are a really good example of this. When fireworks are created, they actually use different sorts of chemicals to place in the firework, and when it explodes, it glows a specific color. Signs at a store are similar also. The opened or closed signs, as you pull the string, electricity goes through gas that's in a tube and it glows a certain color. Visible light is a type of electromagnetic radiation, and it's a form of energy that exhibits wave-like behavior. In previous classes, whether it was science or math, you should know that waves are described by several characteristics. The first characteristic is a crest, which is where the height or the top of the wave is. The second is a trough, which is where the bottom of the wave is. The third is the amplitude, which is the height of the wave from the resting position. And the fourth is a wavelength. And wavelength is measured to include a full crest and a full trough. And you can do that from trough to trough, because this is half a trough, one crest, another half a trough, which makes one full. You can measure crest to crest, half a crest, a full trough, and another half a crest. Or you can measure from the beginning of a wave, where it crosses the resting point, through one full trough and one full crest, to the end of the wave. So there's three different locations you can measure wavelength. And something that's related to wavelength is called frequency. And frequency is the number of times you see a wave per second. So as wavelength increases, as wavelength goes up, you actually see less waves, so your frequency goes down. So if we have this first wave in the picture, and we increase the wavelength, so we start here, and maybe draw that as our example of a wave. This is one full wave in the distance where we have two waves of our previous drawing. So as wavelength goes up, frequency goes down. As wavelength goes down, inversely, frequency goes up. Frequency is measured in hertz. Capital H, lowercase z, because frequency is the number of waves per second. So hertz is actually 1 divided by seconds. So we can use this information to do calculations. The speed of light is the product of the wave's wavelength and its frequency. No matter the color of light, the speed is always 3 times 10 to the 8 meters per second. So c is always 3 times 10 to the 8 meters per second. Lambda is a wavelength, and that's measured in meters. And v is the frequency, which is measured in hertz. And remember, these two variables, we can use prefixes, so if you see kilometers, you should convert back to meters. If you see kilohertz, you should convert back to hertz. And that's just using the King Henry died by drinking chocolate milk steps to bound the decimal left or right. Every single light combined creates white light. So this prism is an example of white light being bent into the individual colors. Think Pink Floyd, think about a rainbow, whatever you think of, think about white light enters, and the smaller distance across only bends the light a little bit, a larger distance bends the light more, and that white light creates all the colors of the spectrum. White light contains all wavelengths and all frequencies of visible light. So here are the differences in the light waves. Red waves have a 650 nanometer wavelength. Orange waves have 607 nanometer. So since the wavelength is going down, the frequency is increasing. Yellow is a little bit less, green's a little bit less. And then when we see violet, Notice how close the waves of violet are compared to red. Red is actually the lowest energy light. Violet is the highest energy light because there are more waves in the same area. So what we're going to do is look at a couple sample problems. The first one is determine the frequency of red visible light, which has a wavelength of 650 times 10 to the negative 9th nanometers. So we have C equals 3 times 10 to the 8. We have lambda, which is wavelength, which is 650 times 10 to the negative 9. And we have frequency, which is our question mark. And C equals lambda times V, 3 times 10 to the 8th equals 650 times 10 to the negative 9th times frequency. Then we have to divide both sides by that 650. Those cancel out. And V, or our frequency, is left as 4.61 times 10 to the 14 hertz. So notice, with these answers, we are going to have exponents. It's not going to be an easy, pretty number. We are going to have those times 10 to the somethings in order to indicate it. So we're going to use the same equation, but now our wavelength is 420 times 10 to the negative 9. So C is 3 times 10 to the 8. Lambda is 420 times 10 to the negative 9. And knowing that our wavelength is going down, our frequency should be increasing. So 3 times 10 to the 8th equals 420 times 10 to the negative 9th times frequency. Divide both sides by 420 times 10 to the negative 9th. And frequency equals 7.14 times 10 to the 14th hertz. So that's a higher number since our wavelength decreased. So Mr. H catches the news on 7:80 a.m., which broadcasts at 780 kilohertz. Determine the wavelength of these radio waves. So just like visible light, radio waves have the same speed, which is C equals 3 times 10 to the 8. 780 kilohertz is our frequency. In kilo, we actually have to convert back to regular hertz. So to go kilo to regular, we jump 3 places to the right, which is 780,000 regular hertz. So C equals lambda times frequency, 3 times 10 to the 8 equals lambda times 780,000, and our wavelength is 384.62 meters. Even though some of these numbers are large and we have these exponents of times 10 to the 14ths, we're still able to do simple math, either multiplication or division, in order to solve for an unknown variable. So just like previous units, when we use our capital double E button, the second x to the minus 1 button, you're going to want to do the same thing here just to ensure that you don't have simple math errors. So when I see you in class tomorrow, we're going to practice with these equations. We're going to work with the speed of light and how light differs based on wavelength and frequency and solve for unknowns. So I'll see you then.